Hello, construction leaders aspirants. Welcome you all for today's webinar. This time we are come back with the topic bridge design. Firstly, I would like to give a brief introduction about construction leaders. The founder and CEO of construction leaders is Mr. Rajkumar Peninti. As a part of social responsibility and with good intentions, Rajkumar has started the construction leaders platform. The main aim of the construction leaders is to train and nurture students, professionals for the civil engineering society by providing technical knowledge and practical skills. So far, Mr. Rajkumar Peninti have interacted with more than 26,000 civil engineering students and try to create awareness on current practices in the industry and various opportunities for a civil engineer in both the public and private sector. Construction leaders is for to build professional leaders for the construction industry. Now, I feel honored to invite our today's speaker, Mr. Uzma Khan. Mr. Uzma Khan is a structural engineer expertise in bridge design with over 7 years of experience. Mr. Uzma was a part of the bridge design that designed in Pune and Bombay elevated metro projects in India and has a decent experience in analysis and design of construction structures, including multi-level station pipes, box girders, glaze analysis, to name a few. He is currently deputing his responsibilities as a head of engineering operations for a construction company in Doha, Qatar. He holds a Master of Technology degree in Computer Aided Structural Engineering from IIIT Hyderabad and Bachelor's in Civil Engineering from MIT. He is also the founder of Bridge Hacker and dedicates his spare time to design curated content on bridges for students and professionals worldwide. Thank you for joining with us, sir. Over to you.
Hello, hi. Am I audible?
Yes, sir.
All right, all right.
Yes, sir.
So, shall we begin the session?
Yes, sir. We can start, sir. Yes.
Okay, so my screen is visible to you?
Yes, sir. Yes.
All right, all right. So, we shall begin the session then.
Yes.
Hello, good evening to one and all. This is Osama Khan. I'll be presenting the webinar on the design philosophy of metro bridges. So we shall start this session. Okay. So first of all, a brief introduction about myself. I'm as as our host, Ms. Chaitanya Siresha introduced me. I'd like to add up, I'm currently deputing my responsibilities as the head of operations, engineering operations in Doha, as well as I was a part of the design team that delivered the Bombay and Pune metro projects. Okay. Apart from this, I also founded BridgeHawk. BridgeHawk is a platform, okay, not a company yet. It is a platform that dedicates itself to reimagining the concepts of bridge engineering. Okay, so what we basically do is that we try to present the design aspects of bridge engineering to students and professionals in a way that they can better understand it. Okay, so you can follow BridgeHawk on YouTube and on the website. All right. So without much ado, I'd like to start. So with the basic question, what are bridges? Okay, so bridge typically is a structure which is built to span a physical obstacle. Okay, and this is done without trying to block the way underneath so that the traffic keeps on flowing beneath it. And the bridge also delivers the vehicles above. It is also constructed for the purpose of providing a passage over the obstacle. All right. So the basic design idea for bridges is that the supports must be strong enough to hold the structure and the span between the supports must be strong enough to carry the loads. So with this basic idea in mind, all the components of bridge are designed. Okay. In order to achieve this design, there are a number of codes. Okay. We've got American codes, British code, European, as well as we've got an Indian code. Okay. So based on what region you are trying to design a bridge in, it is going to define what parameters and what codes that you're going to follow. Okay, so the design process can be divided into 4 basic stages. The first is a conceptual design. Second is the preliminary, and later on we go for the detailed design and then the construction design. So moving forward, we have different types of bridges. All right, so it depends upon the client what type of bridge or what type of structure is required. Maybe some projects might have an aesthetic appeal, and some of them might not. All right. So based on what is the problem statement or what sort of problem is supposed to be solved, the bridge type is decided, and this is completely decided by the client or the government authority, whoever is in charge of the project. So these are a few type of bridges. Suspension bridges. So you've got a big cable suspended with suspended stays, which is holding the girder. This is the Çanakkale Bridge in Turkey. We've got balanced cantilever bridges, Trunnion bridges, which will open for the passage of boats below. We also have tied arch bridges, which is based on the principle of arch which is stressed. We've got arch bridges in a similar way, made up of the arch, which is made up of a steel truss with anchors at both the ends. We also have cable stayed bridges. So the cable stayed bridges, we've got multiple variations of what cable stayed bridges can be. So this is a single stay cable bridge. This being a double stayed cable bridge. Extra doors bridges, which are somewhat similar to cable stayed bridges, but the only thing is that the pylon is not as long as cable stayed bridges. The girder is mostly a part of the structure. The pylon is mostly a part of the girder. Masonry bridges, which are obsolete now. Steel truss bridges. Trunnion bridges. This is rather a unique style and design of a bridge. Over here, you can see the counterweight. So the basic principle is that basically you just bring the CG of the bridge from here to over here. So when we do this, the bridge will lift up. So I think even this is no more in use. It's also obsolete. A special kind of bridge with a mechanical augmentation, like a lift bridge. It will basically, the central span will lift up. Over here is the machine assembly. Okay. And finally, we'll come to the beam bridge. Okay. So in most of my webinar, for a larger part of my webinar, I'll be speaking upon beam bridges. Why? Because this is one of the most common type of bridges and the easiest to install. And especially in an urban environment, it is highly preferred that the traffic is not stopped, and we have an easy installation of the bridge and a successful launch of the girder. All right, so beam bridges is the simplest and most inexpensive kind of a bridge. And as the name suggests, it is a simply supported beam. All right, so we've all designed simply supported beams in our RCC subjects in engineering. So basically the force is going to create compression on top and tension at bottom. So in the same way, we'll have to design tendons and make the beam force tension on this principle. So basically these are very easy to construct and they're widely used in urban and rural zones. The only disadvantage is that maybe when we have large spans, if the span is too long, the depth of the beam might be higher. All right. So in that case, maybe you'll have to go for a different kind of a girder. Okay. And people might not find this beam to be very aesthetically spectacular. Okay. It looks quite mundane, if I may. Something like this. All right. So basically, if going into some detail, basically these are all these, what you see, these are I section beams. And this going horizontally is the bracing, or you can say the central diaphragm. All right, this is put so that we have the girders in place. Okay, this over here is the deck, and these are piers. We'll go into much detail about the design in the slides to come up next. So now coming to our main topic, metros. So what are metros? So basically they're actually called as MRTs, which is urban mass rapid transit systems. Okay, these are elevated railway transit systems with the tracks supported above the street level on a viaduct superstructure or any other elevated structure. So the materials which are used to make these viaducts are usually either from steel, from concrete, prefabricated members, post-tension concrete, or you might use a mixture of more than one materials. Maybe the girder might be of steel and the deck slab would be concrete. Okay. So if in most cases, if you are using a I section, which is a steel I section plate girder, mostly what we'll have is a concrete girder. If you have a I section steel girder, you'll have a concrete deck. Okay, so in that way, this would become as a composite bridge. This would be categorized as a composite bridge. So in our future further slides, we've got some design philosophy which will deal with composite bridges also. All right. So basically, if we look at the structure, it can be divided into three different parts, which is a substructure, a superstructure, and the foundation. All right. So yes, I believe many of you might have traveled in metros. So usually, what the distance between two stations is kept at 2 to 3 kilometers. All right, and I'll share some more knowledge about this in the further slides. Like for example, if you've got a city, and we have to create a layout of metro lines. Okay, so what we don't do is that we don't take a single metro line that goes and traverses all the important locations. Okay, so the basic idea is to have different lanes that go around the city so that they provide easily accessible transport to everyone. It is also called as multimodal transportation system. Multimodal is that, for example, in order to get to the metro station, you'll take a bus. Okay, so now you have used the bus to be transported to the metro station, and now you're taking the metro to go wherever you want to go. All right, so you're now, in order to reach your destination, you have used two different modes of transport. So this is called as multimodal. Okay, so the idea is to have, okay, so the idea is to have different lines and to place different stations at different lines and to create junctions. So for example, as of now, if you see over here, we've got a green line, we've got a yellow line and a blue line. Okay, and these are stations. So as I mentioned earlier, the distance between two stations is usually kept at 2 to 3 kilometers. Okay, and these lines, these are, you can say this is the center line of the track. Okay, so maybe this might be 2-track metro system. And just imagine if you were to have a single metro system that goes everywhere else, you will need to have multiple number of railway tracks. Okay, so once you do something like this, so people can change their destination, the lines on junctions. Okay, so these are normal metro stations and these are junctions. So basically, if you see, the cities which recently might have had metro stations are quite resolved. They're easily, what you can say, mappable. So this is, in front of you are two metros. This is Doha Metro and Dubai Metro. So if you can see, Doha Metro is divided into 3 lines, red line, green line, and yellow line. And over here in Mushrib, you've got a junction, wherein you can go from either from yellow line to red line or to the green line. At Al Bidda station, you've got a junction by which you can, coming from somewhere over here to somewhere in Al Bidda, you can change and you can go to a different line. Similarly, in Dubai Metro, you can have, over here we've got 2 lines. I believe this is the orange section. I believe this is the tram, and these are only 2 lines. So this is quite simple. But why? Because these are planned cities. These are new cities. But if you've got historic cities, the configuration usually becomes a bit more complicated. Like Delhi Metro, if you see over here, you've got multiple lanes, and part of it is also underground. Maybe there's also a transition. I haven't been able to travel in Delhi Metro, but if you see over here, it is quite a hodgepodge. All right. So over here, if you imagine that this is a city which is actually, it's a living city. Okay, so it is very important that whatever construction methodology you're using, it ensures that
11-5 to Toronto.
Hello. Hello. Okay. So whatever coming back. So whatever construction method you use, it should ensure that the city does not get stopped. Okay. That the roads are still functioning, and the least amount of infrastructure has to be disrupted. Okay, so in that way, it is very important that a certain specific construction method has to be chosen. All right, that is why it makes simply supported systems so common and so favorite of everyone. All right, so over here is the general arrangement drawing and the general elevation drawing. As I said over here, that the layout has to be divided into different lines. So you can assume that I'm talking about a certain section of the layout. Okay, maybe I'm talking about this section. Okay, so before we can design anything, we need to have this drawing with us. Okay, so before the general alignment of the track has to be decided, an extensive survey is performed, a survey which includes all the details that might be helpful for us to design a metro system around a city. So this actually is a drawing of a flyover in Indonesia. Of course, for confidential reasons, I cannot share the drawings of the metros I've worked upon with you. So, but this as well does the job. Okay, so over here, what you see over here is this is the approach slab. Okay. So typically in a metro system, we don't have such an arrangement of an approach slab. Okay, but these are the piers. If you see over here, the piers are named. This is A31, PB30, PB1, PB2, PB3. So PB is indicative of portal beam. All right. Each of these piers in the plan over here, you can see each of these piers have been named and the distances have been marked. So over here, what we see is that between pier PB3 and PB4, you've got a distance of 25,000 meters. Over here, we've got 3,000 meters of distance. Similarly, over here, we've got 3,000. This is showing the direction of as exactly where it is going. So in order for us to understand exactly what sort of foundation we should use for these piers, we should have a very resolved idea of what is the ground condition. What does the ground look like? Or what is the safe bearing capacity? Where is the water table? Where is the rock? So these details need to be at hand. Okay. The most important thing in determining this is exactly what is this safe bearing capacity of the soil and what is the rock. Like for example, if we've got a rock which is starting directly over here. Okay. This is the ground level. So we can think of having an open foundation. And maybe if the rock is well below and this is all sandy gravel, so maybe we'll have to go for a pile foundation. Okay. And even maybe have inclined piles. Okay. So over here, you can see this is a layout, the general layout of the project in a city. Okay. So as I said, the type of bridge, the type of pier, the type of girder, everything has to be specified by the client. All right. So if we've got like public works department of any state in India, which is like, for example, it is planning for having a metro station in Chennai or maybe in Mumbai. So this authority must give you a design basis report. So what is a design basis report? So this report is, you can say that is the single most important report before you begin any sort of designing. So this is typically a report which specifies everything that the project would actually require in order to find its completion. So before starting any project, a well-defined design basis or a design requirement criteria, in addition to a well-defined scope of work, has to be set forth by the client. So this client, he must tell you exactly in this report, what is this project, where it starts from, what is the scope of work of the contractor or the detailed designer, and what type of a project are we looking up to at? Is it a cable stayed bridge? Does it also have extra dose bridges? In between, do we have a span which is curved? Do we have girders which are made up of steel, or do we have only concrete girders? What type of launching method is used? What type of formwork is supposed to be used? Okay, So this documents the rationale, the criteria, principles, assumptions, constraint used for the detailed design engineering and the final designing of this product. Okay, so this document must provide you with all the principles of design. It should also specify what code you should follow, what is the grade of the concrete that is going to be used for the pier, for the foundation, for the pile foundation, for the pier cap, what is the type of bearing, is it a neoprene bearing, is it a pot PTFE bearing, if we have got multi-cell box girders, what is the what would be the geometry of this design of this girder? Everything it should specify. Okay, so it is essentially a set of conditions, requirements, needs of the project, and performance criteria. Okay, so this should include concrete and steel grades, type of girders, construction methodology, what are the tolerances, what is the section geometry. For example, if you have got piers, what are the aesthetic visual, they should share with you the visualizations, the concepts, the test required, load cases and combinations. Yes, this is also an important point. All the load cases, they will specify, okay, we need a load case and your design should specify or satisfy this certain load case. Your design should comply with this codal load cases and combinations. They'll say, okay, whatever you design, the combination should be used from American code. The combinations will be used from this certain code. So the designers has to comply with the DBR 100%. Okay, it is the responsibility of the detail designer to comply with everything on the DBR. Okay, it will also specify the permissible speed of the metro bogie. Okay. Okay, so as I told you that over here, that in order to have a proper idea of what the ground below this structure looks like, we need to have multiple surveys. So one of the surveys is having a soil bore log. So soil boring is a practice of geotechnical investigations, the purpose of which is to determine soil load bearing capacity. Okay, so this will help us understand what is the chemical contamination below. Does the rock start quite early, or if the rock is too deep inside? Where is the water table? What type of soil? Are we dealing in? So it provides key pieces of information like bearing capacity, type of soil, cohesive soil, is it a non-cohesive soil? Where is the water table? Lithology is the study of rocks, the rock profile. So over here, once we have the survey done, it will give us a report like this. So before proceeding in designing anything, the soil bore log should be at hand. All right. So this is the bore log at only one location. Maybe like, for example, over here, if we saw, these are so many different piers. So let us say, okay. So let us say this is the bore log of location PB3. Okay. So what this basically tells us is that over here is the depth of ground level. So what this basically tells us is that the ground below PB3, okay, up till 1 meter, it is mixed pebbles. Okay. Below it,
excuse me, sir.
Yes.
Sir, the screen sharing is stopped.
It is stopped? Okay.
Yes, sir, it's stopped.
Now it's okay?
Yes, sir.
All right.
Yes, sir.
Okay. All right. So what this basically tells us, okay, like for example, if this is a bore log for location PB3, I've taken it from over here. Let us say this location. Okay. As of now, we are trying to design this pier. All right. So we need to know the exact conditions below this, this pier. So what we'll do is we'll go to the soil bore log. And basically what this log tells us is that just below PB3, the ground up till 1 meter is mixed pebbles. After that, for another 1 meter, we have got sandy clay. And then for 2 more meters, we have got clean sand. And below that, it is all coarse sand. So this gives us an idea as to what would be the safe bearing capacity. Also, there'll be one more, there will be many columns, but one of the columns would be SBC. It will tell us what is the SBC and what would be the design SBC. So they will maybe tell us, okay, at this location, use SBC 250. Okay. So this would be a third party concern. We as structural engineers are not required to go into a lithology. This will be done by a third party and it will be given to us directly. Okay, so this will enable us to design foundations, and even if we are designing a open foundation, it is very important. SBC is very important. And this helps us understand what is the strength of the soil below, what is the bearing capacity of the soil below. All right, so moving further, this is a typical sketch, or you can say a typical elevation of what a metro viaduct looks like. So as I've indicated, there are different parts to it. Okay, this being the transverse side. Okay, this is the transverse section. This is the longitudinal section. So over here, what we have used is a multi-celled box girder. And this is actually, this has been taken from a live project. Okay, so for obvious reasons, I cannot share the drawing with you. So I've made a sketch for you people. So basically coming from bottom to top over here, we have used pile foundations. Okay, in order for the load to be distributed properly, we'll have to use a pile cap. Just below the piers, we'll have a crash barrier. What is the role of crash?
Excuse me, sir. Good evening, sir. This is which is the more better? This is a multiple box girder or single cell? I mean, which is more, because in the normally it is said in the construction that single cell is more compatible and as well as easy to construct. So
that is
just
right.
kindly.
That is right. Okay, but it is better that we take questions at the end so that I can be in a streak of explanation. But still, multi-cell box girders, of course, it is much more difficult. Multi-cell box girders are usually used when we have got multiple tracks. Okay, like for example, we've got a wide viaduct. Okay, we've got a huge bridge. If the width of this girder has to exceed a certain limit, we'll have to use multiple cells. Like for example, these are called as cells. Okay, so if for example over here, this is track 1, this is track 2. So if I need to have more tracks over here, maybe if I have track 3, so it would not be accommodated. So maybe I'll have to go for a wider girder. This is the wing wall. Okay, so I'll have to have a larger cantilever over here. So if I have only 2 tracks which can be accommodated on this level, so I don't have to go for a additional cell. So I can directly have a single cell box girder. Okay, so of course multi-cell box girders are more difficult. Okay, secondly, as we were discussing, crash barriers. So the role of crash barriers, we'll deal with this when we are talking about loads. Okay, this typically is the pier. As I said, the DBR has to specify what is the shape of the pier. Is it a circular section? Is it exactly rectangle? Does it have chamfered edges? Is it maybe does it have multiple piers? Everything has to be specified by the DBR. Even this architectural curve, every aesthetic element has to be specified by the client itself. Okay, of course, the detailed designer can say, okay, the capacity is not matching, so maybe I'll have to change the section. Of course, you can change it. Over here is the pier cap. Okay, this is a section, section that is coming like a flanging section. Okay, so this is called as a pier cap. It's a bearing. Bearing is one of the most important aspects, and hopefully, if we have another session on detailed design, I'll shed some more light on what sort of bearings are used for what sort of spans. Okay.
So bearings, sir, we require the spherical or in this normal pot and pot PTFE?
Well, that depends upon what sort of restraint you want, what sort of support condition you're trying to have. Okay. So most possibly, when we are having a simply supported span, it is going to be either a neoprene or an elastomeric bearing. Okay. This is rather an important and unique phenomenon of the piers. This is a seismic arrestor. What these seismic arrestors actually do, we'll discuss in later slides. This is the box girder, multi-cell. This is the left-hand side span and the right-hand side span. These are crash crash barriers or crash parapets. These are rail pedestals. In a moment, I'll also show you a 3D model so that it will be much more clear. This is a bit more detailed sketch. Okay. One of the main concerns of a designer when he's actually trying to design or when he's actually trying to transfer the forces to the bottommost part of this structural arrangement is that he needs to know what are the different levels. All right. So over here, I've marked these. I've marked all the important levels that you need to consider. Okay. So I'll also let you know why these levels are important. So if you can see over here, I believe, okay, this is clear, right? Okay. So from over here, if you see, this is the top of pier. As I told you in the previous slide, the pier stops over here. Okay. Now this is the pier cap. So this is the top of pier level. This is the centroid of the pier. You need to know this. Top of pier cap, top of the pedestal, okay, and the top of bearing. Centroid of the girder. What is the level of the centroid of the girder? Okay, because if you've got any moment, it is actually rotating about this centroid. Top of deck, top of rail. Okay, what is the rail? This is the rail upon which the axle load is going to be directly incident. So you need to know what exactly is this level. And the center of bogie. Bogie is the metro, you can say metro rail. So what is the centroid of this bogie? Okay. Apart from that, some of the other levels is like centroid of the vehicle. Why do we need a centroid of the vehicle? Is because, as you know, this is a crash barrier. Okay. So when a vehicle is going to hit this crash barrier, we need to understand at what point is the force centered as to what is the point that is centered around, so that we can calculate the moment and the force impact. Top of pile cap, bottom of pile cap, and pile cutoff level. This is the point at which we stop the pile. Mostly this is stopped when we encounter a rock. Okay, or if it is a friction pile, then maybe it is a different case. Okay, also, if in case your structure happens to be in the vicinity of a water body, or it is assumed that maybe in this zone, there is a threat of having excess rain, or the water is, it is anticipated that it is going to experience waterlogging, or there is a river besides it. So it is important for us to know that what is the low flood level and what is the high flood level, and also what is the ordinary flow level. Okay. So, but if we have got, but if you're designing structures which are not threatened by water, you don't need to consider this. We can have a dry analysis. We don't have to consider a wet condition. Okay. All right. So I'll show you a 3D model of a pier. Okay, so this is a model that I created in Shaper 3D. This very much indicates everything that you can have in a typical pier. Okay, so as we just saw, the arrangement comprises of piles, pile cap, crash barriers, the pier cap. Okay, so this is the pile and the pile cap. Coming up, it is a crash barrier. As of now, this is a circular section for the pier. Okay. Then the pile cap and above it is the assembly for bearing. And the red member that you see over there is the seismic arrestor. Okay, and the holes that you see over there are the holes for sleeves. Okay, these 4 holes that you see, these are sleeves which are given in order for the launcher to fix itself. Okay. So we can have different pier sections. As I said, it is the requirement of the client completely as to what is the type of pier he wants. All right. So in this site, the pier assembly that you see, these are the piers that were typically used in many parts of Mumbai Metro and Pune Metro. If you see over here, this is a pier, the crash barrier, and a post tension pier cap. Over here are the cables, if you can see. I'll show you in a moment. And these are U girders. Okay. And we can have any number of variations, and we can have different shapes for piers, as long as you can structurally prove it, as long as you can structurally validate it. All right, so this pier over here, what you see is that the pier has been casted and the reinforcement has been left in order for this precast pier cap to be fixed upon it. So if you see over here, the pier is a separate entity. It has not been monolithically constructed. The bars have been left in order to achieve fixity between the pier cap and the pier. So this is the 3D model of the pier. And later on, the pier cap has been lifted and simply placed upon it. Okay. So this is rather a unique case that we had encountered in Mumbai Metro and Pune Metro as well. So what you see in front of me is a rather simplified sketch of what we did. And if you see that we have got two different types of girders. One is a box girder on the right-hand side. Another one are a batch of concrete I-section girders. So they are both hosted upon the same pier cap, and this is a cantilever pier cap. By cantilever, what I mean is that if you see, this portion is rather elongated, and it's like it is under the cantilever behavior. Okay, and we've got different types of piers. We've got RCC piers, we've got piers with post-tension pier cap, we've got hammerhead piers, cantilever piers, something like this, portal piers. I'll show you what that is, and coming down with station piers. So basically, while we were designing this, I'll show you what we encountered as a challenge. So if you see over here, this is a sketch that indicates post-tension pier cap. I've taken a longitudinal section for this. Okay, so over here is the pier zone. Okay, okay, over here is the pier zone. You see, this is the pier zone indicated by dotted line. After here, this zone is the cantilever zone, and as you saw over here, this portion, these two bearings, they are holding a box girder. And these 1, 2, 3, 4 bearings are holding I-section girders. So all the weight, all the moment, everything that is that this deck is actually experiencing have to be transferred by the way of the girders to the bearing. Okay, so bearing is the central interface between the superstructure and the substructure. Okay, so these 4 I-section girders, okay, incident upon them, these are the load values or moment values or horizontal force values which are incident upon this bearing, and this is the seismic arrestor. Okay, over here. So if you see over here, I've tick marked 3 point load, but I've crossed this 4th one. If you see, like if you can imagine why, is because it is in the pier zone. Okay, so it will not be a part of the cantilever moment that is supposed to govern the design load case for designing the pier cap. Okay, so we have these point loads which are directly incident upon the bearings. So we have a force which is actually acting upon them, and with this subsequent lever arm, okay, if you see lever arm, we'll have different lever arms. So the lever arm is taken with the reference point of the pier face. Pier face, and this is the lever arm. If you see over here, this is the lever arm for the point load, which is P3. This is P2, and this is P1. Okay, so you can say this is lever arm number 3. This extending up to lever arm 2, and this one lever arm 1. So the moment which this load P1 is generating upon the pier cap is M1, which is P1 into LA1. Okay, similarly P2 into LA2 and P3 into LA3. Since this is in the pier zone, this load will not be considered in transverse moment. Okay. Similarly, for the right-hand side, both of these will be considered with maybe LA5, LA6, and this is going to generate a moment. So now the moment from, this is the transverse moment from the left-hand side, and the transverse moment from the right hand side. They're together going to nullify each other, or we will have to calculate the net moment. Like for example, if this is 100 and this is 50, so the net moment is going to be 50. Okay. Similarly, you'll have to design the pier cap for that. So this is only the force. You can say it's sort of a force diagram, but since this is a cantilever pier cap, the extents of these are too long. So for that, we'll need to be designing it as a post-tension pier cap. So this is same pier cap. This is the stress arrangement, cable arrangement. If you see, what this typically is that these are the cables for post-tensioning. These are the anchorages. I've just indicated them this way. These are the distances from the top. And you can say if I've taken a section from over here, or if I see this pier cap from over here, I'll look into this diagram. Okay. So talking about the profile first. So this is the cable profile. All right. So if you see over here, we'll have rather straight profile, and over here we'll have a parabolic curve. Okay. So this is basically done in order to take care of the moment that is going to be generated. That is why the eccentricity at the center point is more. Over here it is less. Okay. This would be the combined CG of the strands, all the strands. We've got many strands. Like for example, if you look at this diagram, we've got about 10 strands with an addition of 2. So what this typically means is the stages of stressing. Okay, when we are stressing any structural member, it has to be done in stages. Okay, why we use these kind of construction stages? I'll discuss this when we are actually dealing with some detailed design. Okay, and we have to also give a provision for future pre-stressing, just in case we happen to encounter a problem that the beam is not being, the cantilever pier cap is not being able to accommodate that much load. So in that way, we'll have to leave two cables for future pre-stressing. Okay. So as you said, these 1, 2, 3, 4, these have been done in stage 2. 1, 2, 3, 4 have been stressed in stage 1, and stage 3 has only 2 stressing cables. Okay. So this has to be exactly replicated in the software that you're using. Basically, what we used was Midas Civil, and we had to try we have to try a very rational approach, and we had to experiment a lot upon what should be stressed first, what should be stressed later. Moving further, these are portal piers. We've encountered these a lot, and basically when we use it is that when the distance between piers, when it is not feasible for us to have a direct pier over here. Okay, as you see over here, there's a different bridge. So we have a limitation that we cannot have a direct pier over here. So hence we'll have a portal frame. Okay, so this typically is a frame like this, and the girder would be over here. And we can have different variations. Okay, like for example, this is pier 1 and this is pier 2. You can have a variation like this. Pier 1 is deeper, pier 2 is much lighter. Maybe the rock is like this, or something like that. Okay, we can have pile foundations for this pier. We can have open foundation for this one, as well as a combination of girders. Like for example, over here we can have box girder. Over here we can have I-section girders. We can have more than one box girder. So it typically is based upon the layout and what is your requirement. So these are, this is a sketch briefly indicating what are the different components of a portal pier. Okay, if you see over here, these are different sections. What is the section of the portal beam? If you cut it over here, you'll get a section like this. It's like a T-beam. This is a cobble section. Cobble section is this one, this zone, which is actually hosting the piering and the seismic arrestor, and subsequently the superstructure, the box girder and the pier section. Okay. If you see closely, this is the cable profile. Okay. the cable profile has to, as I said, has to be modified and has to match the requirements of the moment that is generated. Okay. Yeah, now coming to station peers, this is one of the most interesting elements of elevated metros. Why? Because the challenge exceeds a certain limit in this, because usually station piers are supposed to have an aesthetic appeal. So an architectural consideration has to be also made. Okay. So any station that you might have traveled, you might have seen that it is comprised of many different piers. So one station is supported by multiple number of piers. So maybe this entire station is supported by 8 number of station piers. When we designed Mumbai Metro, it was one station was supported on 10 different station piers. And second of all, I'll also show you how many levels are there to a station pier. Okay. And if you see over here, this is rather a huge shed. Okay. So for this, a separate arrangement has to be made. It should be supported. The load has to be supported sufficiently supported. And so the number of challenges that we face in designing station piers, that goes well beyond a certain limit. Okay. So this is a general elevation for a station pier. It is rather it looks like quite a hodgepodge, but if you see, it is it is more about levels and dimensions rather than components. So if you see over here, they've indicated number of levels. What is the level of this? What is the level of that? Similarly over here, there are some levels mentioned over here. Okay. Later on, there are some dimensions mentioned. So typically, this is your station pier. Okay. This is your station pier. I'll show you the next slide. This is a station pier. Okay. These over here, what you see are the concourse arms. All right. These are cantilever arms which are stretching out from the pier. This is the pier. This is the pier cap. If you see over here, this just has got one level. Over here, we've got number 1, number 2. Okay. There's also one more level over here. So now, having seen this photo, it is easy for you to understand this pier in the context of the architectural drawing. Okay. So now this is your main pier. This being the first arm. Okay, these are the I sections which are supporting the deck over here. This is where the pedestrians are. So these are the stairs. These are the stairs that you take in order to get to the metro bogie. This is the metro bogie. All right. This is the first arm. You can say concourse arm. Over here, the pier is extending. This is a pier cap. The box girder. And finally, over here is a separate arm, which is a platform arm. So this is typically the platform. So this platform arm is supporting the I section, which is supporting the deck, which is supporting the pedestrian. So the pedestrian is going to the metro from over here. Okay. And as I said, all these architectural elements have to be supported. There are huge loads. These generate huge loads, especially wind loads. Okay, so these are station piers as constructed. So this is a typical segmental launching. So these, you can see, segments are being joined and lifted one by one. This segment already casted, and this is the staging arrangement. So this is concourse arm 1. This is, I believe, this is a platform arm. Okay. Over here, if you see, this is entirely post-tensioned. Okay. Since we are talking about huge moments, it is imperative that we go for post-tensioned. Okay. So this is typically a sketch to throw some more light. All right. These are station piers with only 2 levels. This is level 1, level 2. we can have station pier with one more level. I'll show you that in the next slide. So basically, the station pier can be broken down into three main parts: the main pier, the pier above the concourse arm, and the pier above the pier cap. Okay, so this is the main pier. This is the pier above concourse arm. And there's a simple pier over here, which has to be, which sockets this platform arm. This is called as pier above the pier cap. Okay. So I've tried to simplify this as by medium of the sketch. So this is typically a 3-level station pier. Okay. So with pile foundation, this is the pile cap. Do I have a, no, I don't. Okay. So over here we have got a pile cap with piles and a crash barrier, crash parapet. And so this is your main pier. This is the pier above the concourse arm number 1. This is pier above the concourse arm number 2. And this is pier above the pier cap. So why I'm typically showing you this is that you need to understand the number of girders that are actually incident upon the concourse arms. So if you see, this is basically a pier like this. Okay. This is a pier. All right. And the section is decreasing. Okay, that is for obvious reasons, because the axial force is increasing. Okay. So these arms are stretching out from the pier. So these are actually cantilever arms. Cantilever arms. Okay, they're trying to deflect like this. All of them. Okay. So having said this, I'll clear this off. Okay. So if you saw the first drawing, this one, you can observe over here that yes, all of these I sections are going to put on, they're going to put loads upon the bearings. Okay, these I sections are placed upon bearings. All of these I sections will be placed upon bearings. Okay, so whatever the moment and the loads, they are directly going to be transferred on the concourse arm by the bearing. Okay, so these are the bearings. So now you've got point loads all on the bearings. Okay. So as we had seen in the case of cantilever pier cap, the lever arms, different lever arms, similarly, we'll have different lever arms generating a higher magnitude of moment. Okay, the moment, the lever arm will start from the face of the pier. Okay, so we'll have different lever arms, like for example, we can say this P1, 2, P3, and P4. Similarly, we'll have lever arm 1, 4, we have 3, 2, and 1. So all of these point loads, they'll generate a moment. Okay, similarly, they will generate a moment. This is level 1. On level 2, a similar case would follow. We'll have moments. We'll have moments. This would be an increasing magnitude, or it might also decrease. The lever arm is not only the concern, right? Of course, because if the lever arm is more, you'll have more moment. But it is possible that the moment over here, maybe this is 100, and it is possible that this would be 50. Why? Because it is not only a matter of lever arm, but over here, maybe if we have some furniture or if we have got a machine like this, okay, the SIDL load is more. So the point load itself is maybe 1000. Okay, and the lever arm is less. So we'll have a higher moment, and we don't have any loads over here. So the dead load and the live load will not be sufficiently creating a higher moment. So it is highly possible that the moment from this is less than this, regardless of the fact being that the lever arm is less. Similarly, on the pier, platform arm, we'll have a similar case. So this is what makes it so complicated. All right. As also we have a, as you saw, we have a box girder over here. So this will also have loads, okay, as well as moments. If the bearing is not in the pier zone, then it will generate a moment also. So all these moments have, as I said, you'll have to subtract the left and the right moments, and you'll get the net moment. So we'll have to represent all the net moment, whatever is at this point. Okay, and similarly, you'll have to design this pier. Sorry, design all these piers separately with the moment that they have, as also the actual force that they have. Okay, so I've resolved this into a sketch. If you see over here, this is a pier elevation. As you see, this is an axial force diagram. So on the pier cap bottom, okay, over here, this is the axial force. As you're going down, the axial force is increasing. And for the main pier, the axial force is small. So the main pier will be designed for this. The pier above the concourse arm will be designed for this axial force, and the pier above the pier cap will be designed for this axial force. As also, it can be, for earthquake design purpose, it can be resolved into a lumped mass. Okay. So this is the design, you can say, principle of pier caps, regardless of them being quite complicated, but they're quite interesting. Okay, so having said this, if you see the number of components that actually define a pier, a station pier, there are too many. So all of them have to be designed separately. So this entire pier, this has to be a separate design entity. This is one design entity. This is second design entity, the pier cap. The platform arm is a separate design entity. The concourse arm is a separate design entity. The second concourse arm is a separate design entity. So the crash barrier, of course, is a separate design entity. The pile cap and the foundation is a separate design entity. All the bearing pedestals are a separate design entity. It is possible that we'll just design one and we'll apply this for the most critical case, and we'll apply the same design for all of them. The bearing, of course, is a separate entity. The seismic arrestor is a separate entity. So you can see that there are too many design components that actually go into creating the actual submission for a design for a station pier. Okay. All right. So over here, the concourse arm. Okay. The concourse arm. This is a model that we had made for one of the stations. So as I told you that this is a model that I made in MEDA Civil, applying all the loads. These are bearing points, all the bearing points. There's a uniform section. The section is like an inverted T-beam. And you see that the variation is quite high. Over here it is 320. This looks like 74. This one's 180. Okay, so all of these have to be properly represented. This is the moment. As also, if you would observe something, okay, over here if you see, there is a section like an inverted T-beam. So we have got bearings on this side as well as we have got bearings on this side. So both of the sides have got bearings. Okay, so basically we're talking about like a corbel. So this is a rectangular beam. It is treated as a rectangular beam with protruding cantilevers. Okay, so the point load is incident on both the sides. Why? Because we've got a girder over here and we've got a girder over here. Okay, so the same principle will use the net moment and we'll design for it. That is why it has been resolved into the center point. It is just a simple 2D model of which I have assigned the section of an inverted T-beam. Okay. This is a concourse arm, and as you saw in the previous slides, these are post-tension cables over here. These cables have to be represented in the software model. So this is the cable profile, and as you can see at the center, the eccentricity is more. And this is the cable anchorage block, which you saw in the picture. Okay, and there's an interesting procedure to this, and you can see that if we resolve this into X and Y axis and the Z axis, for now I'm taking Z as this. So what basically you've got to do is all these points that you see, these are the points, the curve points. So we are defining a number of an array of points. Rather, we are defining only half of it, and then we are mirroring it. Okay. So all these points, they'll have a different coordinate in X, Y, and Z. So every single point over here, when we are defining a strand, every single point has to have an X, Y, and Z coordinate. And when we have this, we have a inbuilt command for defining strands. So once we put all those coordinates and we mirror it, we can have it this way. All right, so this was about concrete concourse arms. If you are interested in this, we can have a separate session on the design of these amazing cantilever members. Moving on, bridge girders. So what are the type of girders that we actually encounter? So we've got I-section girders, box girders, single-celled and multi-celled, U-girders, steel plate girders, truss girders, and composite girders. Okay, so basically we'll be dealing more with the box girders and I-section girders. So this is the model that I made. This is representing a complete structural arrangement. These are the rail plinths. These are the rails, the metro bogie. These are concrete I-section girders. And the bearings, the bearing pedestals, the sleeves, and of course, the post-tension cables. We also see a hole over here. That is for drainage purpose. Okay, we'll have a slight cross slope to this deck. So whenever we've got rain or we've got any other discharge, so it will directly go over here to a pipe, and the pipe goes way beyond, way below, okay, from inside the pier. Okay, so typically this is a typical I-section girder. This is most common, as we have discussed. Most common can be placed by a crane, very easy to construct. It can be constructed on the site or in the warehouse and brought it via a truck. This is a cable anchorage block arrangement. You see over here, these things. They're actually cable anchorage blocks. So these are the, what do you call it? These are 7-wire strands. Okay, so it is like this. One strand is comprised of 7 wires. Okay, so this is useful in stressing. All right, so coming to the next type of girder, which are box girders. So I'll show you a 3D model for a box girder. This is a model that I made in Reaper. This is typically a multi-celled box girder. So you can see the level of detail, and you can see what are the different components that actually comprise a box girder member. Okay. So these are there are three different cells to the girder, and the protrusions that you see over here, these are the shear keys. These are called as shear keys, which when two different pieces or two different segments are placed, or you can say they are joined, shear keys will prevent the horizontal or lateral displacement between the two pieces. I don't know why it is so distorted. All right, this, okay, the notch that you see over here, this one, this is a notch wherein this notch is supposed to accommodate the seismic arrestor. Okay, more on that when we talk about loads. And this over here is the blister. It is a bit distorted. Okay, these are rail plinths, and these are the rails. how we take the loads, I'll discuss in the load section. Okay, so this was the model that we saw. So talking about the different components of a box girder, if you see over here, this is I've only taken half of the box girder. Okay, this we saw over here, this was the rail plinth, the rails upon which the bogie is going to come. Okay, these were the blisters. Over here is the anchorage block. Okay, these are different cable anchorage blocks. Over here, the shear keys. Again, these are the main cables. The blister, the box girder, the web of which is resting upon the bearing. Okay. Also, this part is called as a top flange, and this is the bottom flange. This is the internal web. These are the diaphragms. And this, as I told you, this is a seismic arrestor. The seismic arrestor basically comes over here in the notch. Okay. All right. So this is a typical reinforcement arrangement for a box girder. This is a bin model for that. If you could observe, the different reinforcements are indicated with different colors. The red one is the top flange reinforcement with red, the bottom flange reinforcement with blue, the web reinforcement with green, and this part over here is the diaphragm. Okay, this is a single cell box girder. As also, these are the cable anchorage blocks, and we need to have an additional reinforcement for to prevent bursting. Okay, when we are applying so much pressure, so we can have bursting of concrete. Okay, so in order to prevent the bursting of concrete, we need to put some extra reinforcement. This is one of the models that we did for one of the metro projects. This is the model which I made in Mida Civil. In the same way that we saw in Concourse arms, we have to define a section for end segment, and we have to define different sections and assign it to a line model. And the cable profile with the respective points with the XYZ coordinates have to be assigned to the line model that you make. Okay, over here, these are the support conditions. Okay, so more on that if we have a detailed lecture on design of box girders. This is a typical box girder formwork. So usually what happens is the box girder gets casted on a yard and then it gets brought up to the site. There's a U-section girder. All right. So about construction methods, we've got segmental launching, incremental launching, crane lifting, and in situ casting. So the photo that you see over here is a segmental launching procedure. This is the main girder. This is a launcher. Okay, so what this typically is doing is that it is pulling up these box girders and arranging them above at the exact elevation. So I'll show you a video. So that would help you understand it better. These are conduits. These are not post-tensioning cables. These are the post-tensioning cables, which are going from within the girder. This is how they are being stressed. So once they are stressed, the excess portion is cut off and sealed. Okay, so that was segmental launching. So as I told you that when we are considering design, we need to simulate every condition that can happen that a structural member can experience. So segmental launching involves the crossing over, or you can say passing over of a very, very big machine. All right, this launcher is huge loads. Okay, so the loads from these launches have to be represented by means of a load case. Okay, so what you say is that if you can see over here, the entire load is directed on these three legs. You can say front support leg, and there's a separate launcher case. There's a separate launcher case which is highly critical when we are designing pier caps. So when a launcher at this stage is only, like for example, if you have to take the launcher case at this stage, like for example, if I name this stage as stage 1, at this stage the launcher is only having you can say the launcher only represents its own dead load. Okay, there are no external loads to it, but at this stage it represents dead load, plus it also represents the dead load of the entire span. Okay, so this launcher load case has to be properly represented when you are actually designing a pier cap, or you're designing portal piers, or for that matter. Okay, so this is a launcher, and this is how launching takes place when you have to have a launching done in a water body. The ships will bring the girders. This is another method. This is the incremental launching method, and this is how balanced cantilever bridges are constructed. One by one, the segments keep adding, and incremental launching is something that proceeds span by span. Okay, so it will take an entire span and it will keep on progressing. Okay, so now we will come to the load section. So before we start design, what is the data that you need to have before you embark upon design? So the basic thing is that when we are trying to calculate the loads, we have to go from top to bottom. And when we are submitting a design, or we have to complete a design, we have to go from bottom to top. Of course, we cannot give them first the design of a pier cap and then ask them, okay, later on we'll give you the design of foundation. That cannot be. So first you'll have to submit the foundation design, and then you'll have to go your way up. Of course, maybe they'll ask you for the design for box girders first, so that they can start their casting in the yard. So that is a separate case. But when you're submitting design, it will have to go from pile foundation to the pier cap, the pile cap, the pier cap, and then the pedestals. So the data that you need to have before starting design is like you need to have the location details. What is the pier number? What is the chain age, the height, the different design levels, the levels that we saw in the previous sketches, the seismic coefficient of the zone, the carriageway details, the type of girder, what is the cross slope, number of bearings, if the span is curved or is it straight. You need to have all these details. As also, you need to know what is the material that is allowed. This you'll take it from the DVR. Is it what sort of a concrete that you have to use? What is the SBC? You'll take the SBC from the bore log. Or type of bearing. What type of bearing is it? What type of a support does this span require? The span arrangement, the section data, what is the pier section, the pier geometry, everything you need to have at hand. So what are the different loads that a bridge experiences? These are mainly classified into dead loads, SIDL, that is superimposed, live load, wind loads, seismic loads, water current load, if you have the structure in the vicinity of a water body, vehicle impact, braking, and temperature. So starting off with dead loads. Dead loads are basically the category of loads wherein the self-weight is to be multiplied and transferred to the substructure. So they are a permanent category of loads. Okay, they have to endure this for the entirety of their service life. the self-weight of the structure is usually calculated by the software which you are using. Okay, so if you want to have if you want to be sure of your results, you can have also a manual calculation done simultaneously. Okay, also there's one more thing that it is not always the case that you'll have equal spans on both sides. If you see the sketch, you have span 1 which is 20 meters and span 2 which is 30 meters. So obviously the loads, if this is the top view, let us assume that we've got 4 bearings. So if it is 100, so maybe this is 50 and this is 50 from right hand side. And when this is 50, then it will be 25 and 25. So depending upon the spans on either sides, right hand side and left hand side, you will have the dead load values changing every time. So it depends mainly upon the type, number and section geometry of the girders, span and length. As you said, type. So you can have a case wherein over here we've got I-section girders and over here we've got box girders. So of course, even if you have got such an arrangement, maybe you've got 4 I-section girders or 5 I-section girders, and we've just got over here 1 single box girder. So maybe even if this being 20 meters, maybe this will have more load. Maybe this will have 500, or maybe this will only be 200. So this can be the case. So it is not only about the span, it is also about what is the type of girders, what is the number, and what is the section geometry. Superimposed dead loads. As I said, the DBR, the design basis, has to specify what is the superimposed dead load which is incident upon the span. So that includes long welded rail pads, fasteners, parapet wall, OHE master, like in one of the models that you saw, which had street lights. Okay, solar panels, if we have a provision for solar panels, cable trays, plinth loading, and others. Okay, so this has to be specified by the DBR. This has to be specified by the DBR. So this is a typical picture of this is one of Dubai Metro. So these are the stations. So if you see on the track, it is not only a plain deck. So over here we've got rails, we've got plinths, we've got some utilities. Over here we have some railings. If at all we've got some street light over here, then it has to be represented as load. Then if you've got conduits like this running, you have to have all of them included in the SIDL load case. So this is the long welded rail. Long welded rail is basically the railway. So this is a case, like for example, if you have got a case wherein it is one of the tracks, like this is track 1. Okay, this is track 1 and track 2. But over here you've got a merging track. Okay, so the over here the plinth, the concrete plinth which is going, it has to merge into a second track. So how you will take the SIDL load case? This is a representation of that. Like for example, the red block indicates a curved track, and the gray block indicates a straight track. So when it is merging like this. So at one point, at the midpoint, you can say, it will almost be like one single plinth. Okay, so why I'm showing you this is because if you have to simulate exact conditions, you need to know, like for example, if one single block is weighing maybe 10 kilonewtons, it is just an example. So over here we've got only the dead loads, which is 10 plus 10. But at this juncture, we have only got 10. Okay, maybe it will have some extension, so maybe it will be 12, not 20. So this has to be represented. Why? We cannot risk having excess loads without any reason. So because we need to have it as a proper simulation, so this should be simulated. So over here, if you see there's one protruding element. Over here it is not. So maybe over here it is 10, but maybe it is only 7 over here. So it depends upon what is the level of detail you want in your model. Okay. All right, so live loads. Live loads are basically the bogie loads or the axle loads that must be specified by the DBR. So the design basis should also tell you what is the axle load, what is the loading that you have to be designing the structure for. So over here, this is a typical metro bogie. that I've indicated over here. These are the axle loads. Okay, 16, it is ton, 16 ton per axle. Okay, so in the top view, one of the wheels is 8 tons, the other wheel is exerting a load of 8 tons. So all these details, all these tonnage values have to be specified by the DVR. Okay. Of course, in the software that you're modeling it, there are some predefined vehicles, but only if it is allowed in the DVR, or if it is the client's requirement, you'll use those. Otherwise, you'll have to define a separate vehicle with these distances. Okay, and make them run on the model. They'll also specify the number of successive cars. Like, for example, over here, I've shown you 4 successive cars. They'll show you, okay, we are only planning on having 6 successive cars, one after the another. So based on that, you will have to define your bogey in the software. Okay. All right. Yeah. So I'll show you a small animation of live loads. Okay. So this is okay. So this is a typical elevation for a pier and span arrangement, girder arrangement. So this is span 1, this is span 2, and we are assuming that we have got only 2 tracks. Okay, so when we have got only 2 tracks, what are the possible number of variations of live load that we should consider? Okay, so this is indicating that over here I've mentioned 8 tons, but this is only for one side. Okay, so it is actually 16 tons per axle. So this is the case wherein only single live load is moving over the span. Okay, this is a train which is moving on the left-hand side track. So this is a case wherein a train is moving on this part of the span, only a single train. So now this is a case wherein 2 trains at the same time are running on the track, but now they have stopped on the left-hand side span, or you can say the span 1. They have stopped on span 1. This is a case wherein 2 loads, two trains have consecutively passing, but they are on the same side of the spans. And now this is the final case wherein both the tracks and both the sides have been loaded. So these conditions have to be properly simulated. Okay. Moving on. You need to create possible combinations of live load. So for example, if you see this image, you will realize that there are only 2 tracks, this track 1 and the track 2, but there's also a merger of track. There's also merging track. So this gives rise to a number of variations that the span could possibly experience in its service life. So this was actually a span which I designed for North Mumbai Metro, and this was you can say the number of tracks that I experienced. So this is a trapezoidal span. Okay, and on the trapezoidal span, we had 3 number of straight spans. Okay, so these are straight spans, track 1, 2, and 3. But we've also got mergers. This is track 4 and 5. So now you need to properly simulate and prepare as load cases all the different track conditions that could possibly be experienced by the span in its serviceable life. So having done that, these are the possible variations. So we'll assume, so all of these are live load cases. Okay, you have to create all these live load cases in the model. In my case, I did it on Mida Civil. So we are assuming that only a single train is going on the bridge span. So this is case number 1, T1. Single train is going on track 2. This is T2. And similarly, it is on track 3. It is going on track 3. It is only T3, on track 4, and on track 5. So these are single train load cases. On double train load cases, we can say that, okay, T1 and T2 at the same time, 2 trains are running on these tracks. Similarly, all these variations have to be taken in consideration. And the main cases, 3 trains are running at the same time. So tree 1, 2, and 3, all of them are occupied at the same time. So all these cases must be properly represented. So it makes up total to, it gives us like 14 variations. So these are 14 variations, which will possibly present us with the challenge of finding out what is the highest value of torsion, what is the shear, what is the reaction, the bending moment values for which we should design a different girder sections. Braking and traction rule also. when a vehicle is stopping on the track, it will exert a longitudinal force, as well as when a vehicle is starting off from its rest position, it will also exert a certain load. So it is taken as 20% of the live load. Wind load, like you'll have to refer to the wind load Rose diagram of that area to get the exact value of the highest wind speed. And similarly, you'll have to put the load on your structure. Okay, this we had discussed. Okay, finally, we have got earthquake loads. As I told you, that seismic arresters are a unique member which is based upon pier. So basically, what the seismic arresters do is that they bear the impact of the transverse loads. Okay, seismic arresters are responsible to bear the impact of transverse and longitudinal forces. So depending upon what direction of forces they are actually resisting, they are called as transverse seismic arresters or longitudinal seismic arresters. Many times you can also have a seismic arrestor which is resisting earthquake loads in both the directions. It is doing a job of a longitudinal as well as a transverse seismic arrestor. So that would be called as a of course, transverse and longitudinal seismic arrestor. So more on this. I believe you remember the model that we had spoken about that I showed you upon it. That was a seismic arrestor. I'll show you one animation wherein it will be clear as to why exactly we are considering seismic arrestors. Okay. This is a small animation for different forces on a pier. Dead load. We have studied about this. Self-weight coming from the top, the box girders, the pedestals, the pier cap, the pier, crash, and the foundation. This is the wind load diagram. Wind on the superstructure. It can be resolved into uniformly acting force. Okay, the geometry has to ensure that most of it is deflected. Wind is also impacting upon the bogie. Yes, this is the impact force. Why do we need crash barriers? This is why, because it is possible that a car might actually dash. So it is important to consider this load case. Live loads we have seen, seismic loads now. Okay, if you see the sections, longitudinal and the transverse section, in between we have got the seismic arrestor. So the girder is actually trying to hit the seismic arrestor. I've over-exaggerated the condition, but it would not be so high. It would be in some mm maybe, but I've exaggerated in order for you to better understand this. Okay, this was the longitudinal impact. So if we have a seismic arrestor which is taking the longitudinal impact, it will be called as a longitudinal arrestor. Similarly, for transverse, if it is taking a transverse impact, it will be called as a transverse arrestor. And if it is doing both, then it will be called as a transverse as well as a longitudinal arrestor. Water current loads also. Okay. So this is why we have seismic arrestors. So when we are actually designing a seismic arrestor, this is a case for an arrestor being a transverse as well as a longitudinal. So this is a longitudinal force which is acting on the section, the height of which is 1500, the length is 2000, and this width is 700. So when we are talking about longitudinal design, this section, this figure has to be taken into consideration. So over here, the member is 1500 meters long, but the point at which it is acting, it defines the shear span. So this is your shear span, and this is your depth. So in this case, when the force is acting over here, will resolve the structure from over this part. So in that case, we get 1500 as the length and 700 as the depth of the member. So naturally, it is supposed to be designed as a bending member or a corbel. Okay, if you see over here, we need to know what is the shear span to the depth ratio. If it is less than 6, then we'll design it as a corbel. And if it is not, then we'll design it as a bending member. Similarly, in the transverse direction, this is how the forces and the shear span will be taken. Some additional forces, vehicle collision loads, launcher loads, water current loads, buoyancy, centrifugal, temperature, creep and shrinkage. Creep and shrinkage is basically deformation due to loss of concrete, and temperature loads are due to variations in temperature. So finally, grillage analysis. After having done all of this, you need to know all the load values, and finally you need to create a grillage model. So grillage model is not rather complicated, but rather determining analysis. Grillage analysis can be coupled with construction stage analysis. Construction stage analysis is basically trying to simulate the exact conditions of constructions upon a span. So if you see this figure over here, construction stage 1, 2, and 3. Okay, I'll show you a 3D model so that it is better understandable. So this is a construction stage model that I had made for Mumbai Metro. So this is construction stage 1. If you see properly, you will see that these are girders. 1, 2, 3, 4, 5, 6, 7, and 8. Excuse me. So these are girders. In the first stage, I've activated all the girders. I've activated the bracings. These are the bracings. I've activated the splices. These are the splices. I've also activated all the supports. Over here are the supports. Okay. So this is actually a simply supported simulation. We're basically trying to simulate all the conditions that the span would experience while the construction is going on. Okay. As also, what you need to activate is the geometry, and second, you need to activate the loads. So what are the loads that are activated? The self weight of the girders only. Okay. In the second stage, I activated, if you see, there's some difference, right? So these are the members which are activated. And diaphragm, bracings, connecting bracings. Over here, they were not activated. So why I'm activating this is it is trying to replicate how the construction is going to proceed. Okay. So in this stage, I've activated with, along with the stage 1 activations, I've activated the extended bracings and the diaphragms and the self weight of the added members. This is what I've activated. But in the third stage, I'll have to activate everything. So now it depends upon you as to how many stages you want to go and as to the level of detail as to what you want. Okay. So in the third stage, I've activated the entire span. If you see, these are I-section girders. As also, these are merging tracks. These are merging tracks and these are the girders. And I've resolved them into different segments. This is only to have a detailed, or you can say a more finer result to my analysis. So in this construction stage, I've activated all the geometry. I've activated all the stages, all the loads. So as I told you before, it can be coupled with construction stage can be coupled with different loadings. So over here, we are only talking about the dead load. So we will have 3 different models, wherein like model number 1, 2, and 3. So either you go for a model which incorporates the conditions of the loading conditions of all the 3 cases, or you have a single model. Either you have separate models or you have a single model which incorporates all of them. So in my case, I went for different separately. So in my case, I had a different model for dead load. I have a different model for side AL and for live load. What happens is it reduces the level of complexity in your model. One single model does not have to handle so many iterations or you can say load cases. So I prefer to have different models for all of them separately. So this is the this is the basic of this one. As I said, construction stage, you have to define it. You have to activate, what do we have to activate, and how we go about. Okay. So this is the line model, the 2D grillage model, and this is with the sections. And if you see over here, after the, oops, so sorry. Okay, after the bracing, after the splicing, the section is increasing. Okay, these sections are not as big as these ones. This is because we are at the center point, and we'll have a higher, since this being a simply supported one, so we'll have higher moment on this value. So we'll have a heavier section at this point. So more on this, I believe grillage analysis in itself, a very, very vast topic. So if we happen to have a session on grillage analysis, I'll go in great detail about how we choose a section, how we go about putting the loads, how we go about setting the construction stage and the loading. So more on that when we have a separate session on grillage analysis. So finally, the load combinations, how we go about load combinations is that the DBR has to specify what load combinations you need to take. Do you have to refer to a certain code, or do we have a separate guideline for this specific project? Okay, so typically they'll give you two or three combination like serviceability and ultimate state, as well as to check the SPC. So these are the load factors. So whatever load that you have, like for example, whatever if you're designing a peer, whatever that load you need to create a combination. Like this is combination 1, 2, 3, 4, 5, 6, whatever number of combinations. So maybe at the end, this will give you a longitudinal moment of maybe 100. This might give you a longitudinal moment of maybe 50, 60, or 200. So whatever combination gives you a higher value, you'll take this and design your peer or whatever section you're designing. Okay, so this SLS load case is usually used for checking the structure, and ULS is used usually for designing the reinforcement and other aspects. So yes, I believe this is it. We'll wrap up with this one. So if you are interested, let me know, or you can let the organizers know as to what topic you can say intrigued you the most. You can have a separate session on that. If you want to have a further reading, I'll suggest these 3 books: Concrete the Box Girders by Slides, and this Bridge Engineering Handbook. And the last one is Concrete Bridge Practice, because this is what I referred when I was designing a few structures, and these references. So yes, so if you've got, that's about it. If you've got any questions, then we will be now open for questions for about 10 minutes. Thank you so much. Thank you so much for bearing with me.
Thank you so much, sir. Wow, it's a wonderful session. You have delivered a wonderful practical expertise, what you have gained in your experience, sir. We have never seen this type of session in our webinars. Thank you so much, Osama Khan, sir, for giving your wonderful, for sharing insightful knowledge on bridge design. And I think, and thank you so much, participant. If you have any questions, you can ask in chat box, and also you can raise your hand. We will unmute. You can unmute and you can talk to the speaker. And in the upcoming days, we will also have some sessions with Osama Khan, sir. This is the first session, like a basic session. We are conducting the webinars on bridge design as a webinar series. This is the first session on basics. After that, we will have different topics as are explained in this webinar. We will have different sessions. So please share about our construction leaders, www.constructionleaders.in. So we are doing everything freely as a part of our social responsibility to share the knowledge to everybody. Why? Because if you see in any industry, expert becoming the more expert by learning new things in his subject or domain, but he is not trying to make the expert like him to the society. So we take up this as our part of our social responsibility. Everything we are doing here as a free of cost, everything freely. And as of now, we are conducting webinars, and the upcoming in the next month, we are going to conduct 3 days workshop on site engineering and BIM and everything. So please kindly utilize the opportunity. And in our website, you can take either student membership or employee membership. Both are lifetime free memberships. Only you have to give your details only. So why we kept these memberships are that if any job opportunity, recently some of the HRs are connecting with us. So if any authenticated information regarding the job information also, so suppose if they ask the 3 years experienced structural designers, then we can see in our database who are the 3 years experienced structural designers. So we can refer, and we can share the authenticated information. Not only that, we can share all those things in webinars. You will get the webinar Zoom links through our through mail also, if you register in our website. So we are doing this as our part of service to the society. And thank you so much, and stay connected with construction leaders. Stay tuned to construction leaders, and you can join our WhatsApp groups, and you can follow our LinkedIn page and Instagram page also. So soon we are going to register this platform also as an official training body. So after that, we will give the certificates also, the people who are attending our webinars and workshops and everything also. So we will give the membership user ID and passwords and everything, so you can continue with us. And now, if anybody have the questions, you can ask.
Regarding sir,
And
one
more thing
regarding the grade of the sir.
Just
it
1
is
minute.
better that you first, if you could introduce yourself first, that would be much better.
Yes, sir.
One
This is
thing.
Ajit Pal Singh, sir. I would.
Sorry for disturbing you. Just 1 minute. And in the chat box, we have the feedback form link. Please submit your feedback. Okay. And we have connecting the poll on that. Which webinar you are interested in for the next webinar on structural engineering or bridge design. You can submit your feedback. Everyone, please submit your feedback. According to that, we can go for we will create the content for the next webinar. Okay, you can proceed.
Yes, Mr. Ajit Pal.
Sir. Yes, sir. This is regarding, sir, that normally I'm also having some experience in the railways. We are, but from the client side, there is a one always query. There is a grade like here we are using M60 grade concrete in the box girdle bridges, and we have got the span of more than 30 meters. So just I want to know whether it is got what is the safest minimum design we should have it. Like the concrete grade regarding grade wise. Can we proceed with M45, M50 normal because the quality control is very difficult with the present the caliber of the and it is not the question of the criticism, but it is just because we face the level of the working level of the agency who works. So what is the safest concrete design we should opt for it, sir?
Okay. Well,
like the grade of the concrete, grade of the like M60, they are normally client expectation more that it may not be safe, so we should go to the M50, something like this. So can I just kindly advise about this?
Okay. Well, as I said in my session, the grade of concrete and the type of material that you're going to use is a concern of the client itself. So the client has to tell you the grade of concrete that you should use. So the design basis, when he's actually specifying the design basis, he should tell you what is the concrete grade you should use for the pier, what is the grades you should use for the steel, everything. It has to be specified from the client. So if the client is telling you this, this is somewhat, maybe you can refer to the DBR. So in that case, you can counter this. And of course, we cannot have a straightforward answer to this because concrete grade is a matter of design. So based on based on conditions, environmental conditions, maybe it will change. So based on that, you can counter this question. It is a design requirement, and the client should specify the grade to you. Of course, if the DDC, if the detailed design consultant, if he comes up with, okay, maybe I found this in my analysis to be safe, then of course you can suggest to him. Of course, you can suggest. But as far as girder is concerned, it is more about the moment. So more about the stressing. So if you can prevent the concrete from busting at this anchorage, then maybe you can satisfy the client.
Sir, we have another question that, sir, I have 3 questions. One is the entire modeling of superstructure and substructure is done at a time in one model itself. And second one is how to know our mathematical model is correct or not. And third one is how to model seismic arrestor and give loads to it.
Okay, so the first question was whether you model the superstructure and the substructure combined, right?
In one model itself or not?
No, we don't do that. We don't do that because as I told you in the previous slide, I showed you when we are talking about the station piers. One station pier comprises of different. Okay, I'll get to that portion. Okay. So over here, this is only the superstructure. This entire thing is the superstructure. Okay. Over here, the girders which are going to come, that is, these are the superstructures. The entire thing that you see over here is a substructure. And this over here is going to be the foundation. So just imagine if you model the foundation, the substructure, as well as the superstructure, the model that you will be so complicated. It will have so many load cases. It will have to have so many coordinates for, the tendon profile, the loads which are acting, the geometrical sections. You need to have a tremendous amount of input on that model, and we don't want that because it is not even necessary. Why? Because I showed you when we are modeling, like for example, this is a concourse arm. This has been modeled separately. So if I have a station, if this is one station pair, so my submission of design will be separate for this one. It will be separate submission for this one, and it will be a separate submission for this one. Why? Because the level of intricacy is very high, and we cannot risk having mistakes. So it is preferable, and it is not going to affect your results in any way. And having designing and modeling it in separate software models, it's only going to ease your own result what do you call it? It is only going to resolve your own results. So it is not going to, even if you model it on a single what do you call it, single software file, it is going to create a lot of errors, because you need to be exactly sure of what is, if there's any clash, if there is any error. So the level of error that you can have that exceeds if you have a combined model. So it is usually not the practice. When you are modeling it, you'll have a separate model for every single component. Okay, the second question was, how do we know mathematically if the model is correct, right?
Correct or not? Yes.
Okay, so if as far as the model is concerned, the software is capable of telling you, okay, you have made a mistake over here. Okay, this is the first way of knowing. This is, you can say this is your first line of defense. The second line of defense is reading the results, reading the numbers. So just imagine, I'll give you an example. Okay, so if I've got a beam like this, if I've got a simply supported beam, okay, this is an eye girdle which I'm modeling, and I've got, let's say I've got a bending moment diagram like this, okay, and it is a simply supported beam. So when you are going to export your results, you'll get 1, 2, 3, 4, 5, 6 node. These are node numbers. These are node numbers, and if you get a result like this, or like say 10, 20, 30, then 20 and 10. So immediately you can find out the difference, that it is wrong. Why? Because you know the simply supported beams, it cannot be 0 over here. So unless you get a value like this, you can know that it is wrong. You can know easily that your numbers are indicative of the modeling that you have done. So mathematically, if you want to ensure, you need to have you can say a exhaustive check. Okay, this is a problem that we face a lot while we are modeling. Usually what happens is in Midas, when we have to, in Midas or any of the software, when we have to define a member, it defines like this. Okay, if you have to define a beam like this, it will be defined like this, as like, you can say X, member X, between point 1 and 2. So, but if you want a result at this point, you'll have to define the same beam with 2 different nodes. Okay, 1 and 2, but there'll have to be another node, 3. So when we are exporting your results, you need to be exactly sure as to the number of nodes that you have modeled and what is the concerned node that you want your results to be exported at. Like for example, if this is a bearing point, and this is maybe node number 30, and this is node number 40. So when you are exporting, you'll get thousands of nodes. You'll get thousands of nodes. So you should know that at 30, even if over here we have got minus values of shear, over here you should have a sign change. So that is one way of knowing that your model is correct. Okay, that was your second line of defense. The third is experience. So if you keep on doing this, you will understand, okay, the results are somewhat I'm suspicious of the results. So maybe you'll have to, go back to your results. And what was the third question? I seem to forget. What is the third question?
1 minute.
Sir, how to model seismic arrestor and give loads to it?
How to model seismic arrestor and assign loads to it. Okay, so basically seismic arrestor is not a very complicated entity. Seismic arrestor is, as I said, it is either to be designed as a corbel or it is to be designed as a pending member. So this can be also done manually. Excuse me. So seismic arrestors can be modeled manually. We don't need to have a software model for it, unless and until we have got some very, very extensive load cases going upon it. So seismic arrestor, as you know, it is just like a cantilever, small cantilever beam. It is like 1.5 meter. It is not too much. Okay. So we don't model as far as what I had done. I had never modeled a seismic arrestor on a software, because even as I said, it is a transverse load. It is a horizontal load. We don't have any point loads coming on it directly. I mean, we don't have a point load coming over here. We have loads coming in the horizontal direction only. Okay, so they're not too remarkable to have to be required to be modeled on software. And second of all, it is not a complicated. It does not have a complicated geometry. So this small seismic arrestor can be likened to a small beam. That's it. Finished. It is just like a cantilever structure.
Yes. Is there any particular specification for cross barrier, sir? The question is another question asked.
Sorry.
Is there any particular specification for cross barrier?
Crash barrier specifications? No, not a specific specification. As you know that, for example, if your metro is passing by a highway, okay, the highway speed is maybe 120 kilometers per hour. At the same time, maybe the metro can be passing from a locality which is a cramped locality wherein the speed limit is 70 kilometers per hour. So we cannot have a specific, I mean, we cannot have different values. So what the DBR usually does is that it specifies only for this project. Like you cannot say that a project which has had a certain crash barrier in maybe Dubai Metro can have the same crash barrier in Mumbai Metro. No. So the DBR must specify the the DDC, the detailed design consultant. He will design the crash barrier once for the extreme condition. So if it is 120, maybe he will take 150 kilometers per hour load, and the speed, whatever the moment is coming, he'll design the crash barrier for this high level of load, and it will apply for the entire project. That's it.
Mr. Kassis, you can unmute and ask your question.
Sir, sir, I have a question. When we design for the girder, okay, what suppose we have took M60 grade. So, what is the factor of safety we consider during the design? Like in the simply supported beam, we took 0.36 FCK during the stress calculation. We basically divided by 3 in the working stress method, and the limit state method we take it as 0.36 FCK. So during the design of girder, will it change, or we just took it as 0.36 FCK?
When we are not, yes, we are not, when we are designing, we are not going at the stress block level. Okay, we are not trying to go that deep, because our main concern is the moments. When we are designing a girder, we are more focused upon what are the number of load cases, and we are more focused upon the value of shear, the value of moment, torsion, if it is possible, longitudinal and transverse forces. So this is our concern. Of course, the safety factor can be specific. Yeah, like you can say, okay, I'm taking, when you have an understanding with the client, or if the DBR specifies, you can have a safety factor of 1.2 or 1.5, whatever you like. So based on different structures and the criticality of a certain structure, you can have a different safety factor. But we don't go back to stress block parameters because they are going to remain the same. We are not changing the stress block parameters.
Okay, suppose we are getting a load for which we need some M60 grade, for example. And do we increase the grade, or do we just stick it to M60? I'm concerned about that. Okay, we don't calculate the stress. It's okay, but the grade should be specified according to design, right? The load. So how do we basically determine that, the grade?
Well, see, designing is not only a matter of changing the grade. You've got multiple avenues wherein you can adjust the different elements of your girder in order to reach satisfactory design. So if you're talking about I-section girders, like for example, or if you're talking about, let's say a box girder, if you're talking about a box girder, so the main concern of a box girder is that we need to have this, like for example, this is simply separate structure. So we need to be sure that this moment, okay, this is the high maximum moment, bending moment, okay. This maximum bending moment is actually countered by this cable profile. So this is our main concern. So what happens is the first thing is to know what is the bending moment. So we'll calculate the loads and what is the load case. That is the first thing. So, and the second is, as per these loads, we'll have to create a certain cable profile, and you'll have to have this post tensioning accordingly. So loads are one thing that you cannot change. So this will remain fixed. So one of the main things that we did over there, we did modify the cable profile. So for example, if you've got a cable profile like this over here, so if you've got certain moment, the concrete, because the concrete grade is not a matter of concern that much, because the DBR already specifies to us that if you are doing a box girder, you need to have M60 or M50. So we don't play with the concrete grade. What we are playing with is mainly the cable profile.
So they basically give you it prior to the design. They basically give you that we are going to be designing a box girder with a grade of M50, and then we will have to just design it accordingly, right?
That is right. That is right. As I told you, that we need to have material details, and the concrete grade has to be specified. Even the steel grade has to be specified.
Okay.
Hello. Mr. Irfan Ahmad, you can ask.
Yes, yes, sir. My question is that at the time of designing,
standard guidelines as to what?
any specific guideline? Yes, any guideline for metro bridges. Suppose that any standard guideline from the government or metro department like that.
Yes. We have those guidelines. Like for example, in India, if you are designing metros, we have IRS, and we have got IRS CBC. So these two will specify the, that's a specific, IRS is a specific code for metros. So these will specify. If it is not specified in the DBR, they'll give you a clause. Okay, if this is missing over here, you can go to IRS CBC. If it is missing over here, you can take it from American code. They will specify every single code. Of course, for confidential reasons, I cannot share the DBR with you, but they will specify every single design member in the light of what is supposed to be referred in order to design that. You understand? So you will not have a case wherein the designer is in a quandary that what do I refer to? Okay, you cannot go to, the designer will not say, okay, I did not have any guidelines, so I followed a British code, or I followed a certain European code or a Russian code. No, because these are prestige projects. These are projects with huge capital involvement. So the government has to be, so what the government basically does is that it will have a general consultant, GC. Okay, the GC will tell them, okay, this is what the metro project is going to be like. This is the code that we have to follow for box girders. This is the code we have to follow for pile foundations. The bearing will be designed as per European code. The corbels will be designed as per ACI 318. The bogie load will be taken as per IRS CBC. So everything has to be specified. So if it is not specified, then we'll have a mutual discussion with the client, which is a government body, and we can have, after that discussion, they'll agree upon that. Will agree upon the code or the way to do it.
Hello.
Yes.
Sir, can we use other code also at the time of designing, like European code or ACI code?
Of course, because the design is a combination of having to refer different codes. For example, we design neoprene bearings with European code. We are designing corbels with American code. We are designing the live load is a reference from RDSO guidelines. The IRS CBC will specify what is the tolerance limit. The seismic zone has to be taken from Indian code. So no code is self-sufficient. So when we design metros, we have to have a wide array of codes that we have to refer. But it is always specified. Like when I'm designing a girder, I know which code to follow. When I'm designing something else, I know what code has to be followed.
Thank you, sir.
Sir, to become most of the users ask these questions, to become a successful structural designer, what are the key attributes one should pursue, sir? Or as we have in our construction members, some members are from some students from NIT and IIT, and they are from MTech structural designing students. They usually ask these questions. What are the things we need to pursue?
Okay. So I would say that this is an era of specialization. So if you want to be successful at anything, you have to be a specialist. You don't have to be a jack of all, because we've got a number of people who are jack of all. We don't have specialists. So it is better that you have a certain specialization. So to the engineering students, I would basically say that don't stop at BTech only or BE only. Go for a certain specialization, and don't be a stereotypical, like, it is not only that structural engineers only have a certain edge. Like different reasons have, you can go for water resource engineering and transportation. Even they are good streams, but you need to choose your calling. Like, you need to know what you are passionate about. In my case, I was not very passionate about bridges at first, but later on, when I got to know this domain, I was very passionate about bridges. So first of all is that you need to have a certain specialization, and based on that specialization, you need to join a certain organization which has this which deals in these kind of projects. So many a times the freshers would be faced by high packages, but it is better that you go for a company which gives you high experience rather than a high package. So having done that, you will have more technical knowledge and will be confident in your own domain. Okay, so go for a specialization. We have got many courses. We've got international courses that offer us good amount of detail. They give us a good amount of detail as to different designs. Second of all, I would say that learn softwares. Okay, there is a big what do you call it? There's a gap. There's a big gap of structural students not knowing actually how to do these problems on softwares. So this disparity is actually creating the lack of passionate engineers. So at least you need to know 3 different softwares, and you need to be perfect at these 3 softwares. As of now, we have got different softwares which are good at different things. Like, for example, when we are designing metros, we have only used Midas Civil. So Midas Civil, Sophistic, and maybe Allplan is a new software. These are specialized softwares which have a good interface for bridge designing. If you're going for buildings, ETABS is a software which is very effective. So at least you need to have a command over 3 different softwares, and you need to solve practical problems on these softwares. Okay, it is not enough merely knowing these softwares. You should have the experience of completing and submitting an actual live project. For this, even if you have to do any extra research, you have to do some extra calling or extra effort, you need to put it. But this is the way, because when you know a certain software and you can represent a practical problem in a software, then that gives you a certain confidence that most of the structural engineers that I see do not have. So I believe at least these 3 things that you can do to ace this domain.
Okay, sir. Thank you, sir.
Hello.
Sir, yes, sir. My next question is that, so nowadays, if you see in the industry, most of the people are talking about some buzzword is called BAM, BIM and Revit. So
okay.
Is there any linking of BIM with BIM or Revit with regarding structural designing, sir? Any advancement, anything is there, sir?
Yes, of course, of course. If you, are you talking specifically about bridges or only structural design?
Structural designing and bridges, sir.
Okay, because BIM basically is building information modeling. So BIM has a very, very vast, concern with structures. So if you see Revit, we have got a separate software which we can directly import in. The Revit model can be directly imported to robot, that is Autodesk Robot. And nowadays companies want engineers who can work upon at least one BIM software, that is either Tekla or Revit. And second of all, in building information modeling, there's also something called as bridge information modeling, that is called as BRIM. Okay, so the 3 the softwares that are pioneering this BRIM cause is number 1 is Midas Civil, second is Sophistic, and the 4th one I believe is Allplan. So these 3 softwares are the go-to softwares for BRIM. So that is bridge information modeling. So we have a big scope for that, and projects which are prestige projects usually done in Europe or in the Middle East, they require BRIM engineers. It is not only sufficient to know StatPro or softwares which are not linkable to BIM. They require Midas Civil and BRIM software. So yes, there is a very, very big scope for that.
Okay, sir. And one more question asked by
Sir,
Yes, 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 you can.
sir, please, can you please repeat the BRIM software? I have to note it down.
Okay, the first one that you need to know is Midas Civil. Okay. The second one is Sophistic.
Thank
and
you.
The third one, and
Okay.
All plan.
All plan. Okay. Okay.
All plan. Yes.
Thank you, sir.
Okay.
Yes,
Anything
sir.
else? If
In
anyone
chat
has
box, one question we have, sir.
Yeah.
The one thing is that, sir, any manual methods for analysis generally used in practice, and second one is book referred for FEA, and what is the best way to learn the Midas Civil?
The first one was what? What was the question? Any manual methods?
Yes, sir.
Right. Well, like it begs the basic question: why do you want to go for the manual method when you have got softwares with you? Okay. If the level of complexity increases, doing a manual calculation will only increase your own hassle. Okay. There's a simple. Even if you want to calculate the moment of a simply supported BIM, you'll have to have at least 10 steps or 5 steps. If you can model it directly, you'll get the values, you'll get the different diagrams, you'll get every stress value, you'll get so many things. So even if there would have been a manual method, no one would actually endorse it. Okay. The ones which I told you in the presentation, that if you want to calculate or verify your loads, you can have a manual calculation. That is only for dead load. Okay. Mostly that is used, not only for dead load, but mostly you can have the density multiplied by the dimensions, and you can get the dead load, and that way you can verify that your load is actually matching the load which is coming from the software. But just imagine if there's a live load going on a span and you happen to calculate it manually, it'll take days. So it is best not taking that approach. Manual approach is not feasible this time. So, and the second question, what was the second question?
The second question is that, sir, books you referred for FEA.
Yes, over here you can have, I just showed you the 3 books are important. There are many books also, but these are the 3 books that you should at least have a go through. And the third one, what was
best
the third,
way to learn
third
Midas
question?
software, sir?
Yes, the best way to learn the Midas software is to actually start doing it. You know, literally
Yes,
2 or 3 softwares I learned it out of YouTube. YouTube is a very good resource. We will have directly we have direct access to engineers who are doing live projects. So if you follow the tutorials that they show, literally you can learn any software. So if you are really interested in learning Midas, you directly take up one channel or one single, you can say YouTuber, and you can do all of what he's doing on Midas. And then you go on to the next one, and then you go on to the next one. And I believe in the third YouTuber, by the time you reach the third YouTuber, you would have exhausted all his playlist, and you would have known Midas the way not even 80% of the people know. So if you do this, I believe you can learn any software, and especially Midas, even because that is how I learned it, because no one showed me Midas. And there was only a small guidance from someone. After that, I learned it from YouTube.
Yes, sir. Mr. Nanaji Bolem, you can ask your question. Mr. Nanaji.
No, sir. Thank you.
Okay.
Thank you.
And okay, sir, Mr. Rutvik Bhavaswar asking that can we get any internship programs? Actually, for the internships, we are actually, as a construction leaders, we are trying for the internships, and we have connections also. The only thing is that we have given earlier 1 year before 15 job internships, but we are looking for the serious aspirants. People are going and they are doing like a normal thing. So that's why we stopped giving the internships. We want to give we are thinking to provide the internships for the serious aspirants. So if, we will conduct interview, and we will examine if the candidate is serious. Then we will provide the internships. That's not a problem. But only thing is seriousness is not we are not seeing in the serious aspirants.
If you are serious, there is no problem to provide. Mm. So, and Mr. Osama Khan sir have his YouTube channel and website link we have shared in this, and he has shared wonderful content on his YouTube channel about the bridge designs with the 3D models and like that. So you can go to his YouTube channel and subscribe also. So, and this is the first session, and soon we will have a few more sessions like. Midas software utilization and manual design and box gutter, eye gutter, and some other topics, whatever you suggested in our feedback form. So we are going to conduct soon. And if you like our whatever the work we are doing, please refer our website link or our YouTube channel, or you can tag in construction leaders in LinkedIn also, or by the speaker also. So by that way, people can know the quality content. Though we are doing freely, so everything we want to reach to the maximum people. So there is no commercial angle in this, but we want to reach to the maximum people. So we want to help more people to gain their knowledge and get the professional knowledge and get placed in that. And soon we want to see the more startups in civil industry. So we want to see everybody as a having a own construction consultancy firm. So in the every civil engineer. So this is our future goal. So as a part of our social response we are doing, and here we have said his YouTube channel and Bridge Havak website link also. You can watch and you can follow him. And in LinkedIn also you can follow him. That link also we have shared earlier in this chat box. And thank you so much, Osama Khan sir, for giving your wonderful session. We have learned many things from your
Thank you so
webinar.
much.
And
Thank you so much for having me.
Yes, sir. Thank
I
you.
would like to thank construction leaders. The work that you're doing over there is remarkable. And
Yes.
I would like to thank you, Mr. Pinati Rajakumar, the founder. Thank you so much for having me. And hopefully we'll have different sessions in the time to come based on what is the feedback that we receive. And if anyone wants to have a specific topic covered in bridge design, surely they can share with us so that I'll see how we
Yes,
can.
sir. In that feedback form, we
how
have
we can.
we have given one topic, sir. That we have given that if anybody want any extra session, they can share their views on different sessions or topics which they want
Sure.
to. Yes, sir.
Sure,
And
definitely.
thank you so much, sir. And thank you so much all participants for who are attending this webinar. And if you can join our WhatsApp groups also for the blogs and upcoming things, whatever we are posted in our website, we will post in our WhatsApp groups. So you can connect it with our WhatsApp groups also. If any jobs also there, if you get any jobs authenticated information, we will share in that WhatsApp groups. You can join our WhatsApp group also. So in the chat box, we have shared in our our WhatsApp group link also. Thank you so much. Thank you so much for attending this webinar. Thank you so much, one and all. Thank you.
Thank you.
Thank
Thank
you.
you so much for. Thank you, everyone.